In physics, we sometimes compliment our equations, calling them elegant or even beautiful. Strange, then, that one of the first and most consequential equations in all history turns out to be, well, ugly. Really ugly, especially when we get down to measuring and testing it, which, because this is science, is kind of the whole point. Newton is the namesake of forces, which are proportional to accelerations and, for gravity, inversely proportional to distance squared. And acceleration is change in velocity per time, but you could also think of it as the strength of the gravitational field, which gets weaker and weaker the farther you get from the Earth. Calculus gives us an equation for the distance the apple will fall in a given time, or, if you measure the distance, a way to find acceleration or the gravitational field strength. Hold on to that, and remember that circular motion also means accelerating because the direction of the velocity is changing. Here's a way too quick derivation of the centripetal acceleration equation. Similar triangles, gotta love similar triangles, much more geometry later, and it's a good equation, but it's useless, or at least not easy to use. What, for example, is the speed of this bucket? Well, speed is distance divided by time, circumference, period. And there you go. Accelerating apple and moon. And, oh yeah, the inverse square law, which tells us that this ratio is equal to that ratio. And please excuse me while I tidy things up a bit. You're okay with this step, right? Okay? There. An ugly equation, but one with quantities we can measure. And if you want to plug in values to check my results, now's a good time. But hey, what's that ratio doing there? Why not just keep the distance to the moon and the radius of the Earth separated? Well, two reasons. Measurement and history. And by history I mean the 1980s and this series, the mechanical universe, the gold standard for floating equations. Let's listen in.
The radius of the Earth divided by the distance to the moon squared. That ratio has been known since antiquity. Greek mathematicians calculated the distance to the moon as 60 times the radius of the Earth.
And that is not the only ratio. Times and distances, which means we can use any units we want, miles or minutes, anything, as long as we're consistent. All right, 5 things to measure. The time the apple fell, let's just call that 1 second. But wait a second, what's that? And how are we going to measure it? A second is, approximately, 1/60th of a minute, which is 1/60th of an hour, which is 1/24th of a day. So get your mechanical device like a sundial or a water clock or, fun fact, a 1 meter long pendulum with a 1/2 swing. Next, the distance the apple fell in that time. This is the fun part. Let's measure it. And I know what you're thinking. No need to measure. We can calculate it with the acceleration due to gravity, just like we did in class. But that's the whole point. This time we're trying to find the acceleration. That's the whole ballgame. Period. The time it takes for 1 lunar cycle around the Earth, which might seem simple. Just count the days from 1 full moon to the next. But it's not quite that simple. To be precise, we need to take into account the orbit of the Earth. A full 360 degrees cycle. That's what we want, the kind measured with respect to the distant stars. Now for the good part, the radius of the Earth with Eratosthenes. Take your planet and find a city where the sun reaches the zenith, where it is directly overhead at noon one day. You know it's up there if the sunlight reaches the bottom of the well. The same sun will not be overhead in another city. A pole in that city will cast a shadow, which you can measure. It's all about measurement. In this case, simultaneous measurements, which would be hard to organize, except that we can do them when the sun crosses the meridian on a certain day. Now for the geometry, parallel rays from the sun, and what are these alternate interior angles? And quantities. We will measure the first 3 and then calculate the fourth. More ratios. The arctangent is an anachronism here, but how else would you get the angle? A protractor? And in this step we will switch our calculator modes from degrees to radians, which cleans things up nicely, but not quite nice enough. You may have heard about this trig fact, but that would imply this, and this, and this. In other words, for small angles, like angles less than 10 degrees, sine theta, theta in radians, and tangent theta are all pretty much the same thing. which is useful because we are done. The radius of the Earth now, not from a textbook value, but from the distance between the cities, the height of the pole, and the length of its shadow in the second city. 4 down and 1 to go. But first, let us return to Eratosthenes for a moment. He knew of a city where the sun would reach the zenith. But what if you couldn't get to a place like that? Could this approach work with 2 other cities, 2 different shadows? Rewind to this step, write it out twice, and subtract. The answer, it seems, is yes. All we need to do is make sure we know the distance between these 2 sites and to make sure that the observations are synchronized. Or, since that's annoying, you could forget the sun and focus on the North Star instead. Its altitude is easy to measure, and it never changes. And fun fact, which we'll use again in just a moment. I'm not just telling you everything I know here. We're going to use this again in a moment. The altitude of the North Star gives the latitude of the observer. Makes sense. If you're on the North Pole, the North Star is directly overhead. If you're closer to the equator, the North Star is closer to the horizon. Now on to the final ratio, distance and radius of these guys. Here they are in a photograph from a spaceship. Look closely, there they are. The work is cut out for us here, but if Hipparchus could do it, then so can we, insisting that the distance is measured from the center of the Earth to the center of the Moon, which is the only part of the Moon we really care about. New quantities. And these are the ones we want. And this angle is very small, just a few tenths of a degree. It is the parallax angle. Here are 2 photographs from 2 different observers. The position of the moon changes slightly against the background stars. You know, parallax. Again, we'll put one observer where the moon is at the zenith, and the second observer will measure the angle from the zenith. And I told you that altitude would come in handy. There is a supplementary angle and another useful trig fact. Pop quiz. Who remembers this? I'll give you a second. The law of sines, which we'll use on this triangle. But first, since it's a triangle, we know something about its angles. Or in other words, well, you said that gamma was very small, so that means that theta and alpha are very closely, almost exactly the same thing. Okay, stay focused with the law of sines and one final fact about trig. A symmetry in the sine function, which means that, which means this. Nice. We're looking good. The mysterious ratio has been made measurable with only one small problem. Alpha and theta aren't really that measurable. Why not? Well, what's the problem with latitude? Nothing, really. The problem is finding an exact location where the moon will be exactly overhead, down to the 10th of a degree here. Look down a well, that's one thing, but we need to be precise about what's going on directly overhead. That's difficult. Try to do it yourself. Compared to the size of the Earth, the moon, remember, is far away. Theta and alpha are almost exactly the same. Forget about trying to get the moon to the zenith. Let's just have 2 different cities, and we've seen this result before. A substitution and a subtraction. Delta gamma is, after all, what our photographer friends have already found for us. Fabulous. But what about theta? The thetas would still be hard to find, unless we cheat and observe the moon when it is near the celestial equator. Then it would be safe to use the approximation of theta equals alpha. Hand wavy perhaps, but the latitude and the parallax, those are measurable. Not that it's easy, but it's possible. And I didn't say it would be easy. I said it would be ugly. And it is. Now, the fact that the same force of gravity causes apples to fall and moons to orbit, that's crazy and amazing. But also amazing is how these measurements, they all add together. Isaac Newton wasn't just connecting distant places in the universe. He was connecting back to the ancient Greeks. They measured. They used the same trigonometry to measure different expressions of the same mathematical laws, these perfect laws, these expressions of perfection, which kept working for thousands of years and all over the world as we made all these different, very strange, very disconnected or seemingly disconnected measurements and observations. But this law-like behavior underlying all of the universe, all of nature, was still there. The hidden symmetries, the hidden connections, the hidden potential around us.